Hello, this is Ruth Trigstead with Lesson 1 of College Algebra, also Lesson 1 of Precalculus, which includes college algebra and trigonometry. We're going to begin with an introduction to functions, which is section 1.1 in the college algebra textbook that you'll find in your course. And so Lesson 1, we look first of all at a relation, which you've probably seen before. A relation is a set of ordered pairs, like the set of ordered pairs 2, negative 5, 1, 3, 0, 2, negative 4, 3 that we have here. We look at a relation and we can determine the domain of a relation by looking at the first components of these ordered pairs. So here the domain of this first relation that we have is going to be the set of ordered pairs that would include 2, 1, 0, and negative 4. We can write those in order if we want to. It really doesn't matter, but usually we like things in order. So the set would be negative 4, 0, 1, 2. We can also find the range by looking at the second components of these ordered pairs. The range here would be negative 5, 3, 2, 3. So it looks like we've got 3 twice, but we only need to list that one time. We have negative 5, 2, and 3. And then let's look at one other example here of a relation. This is in chart format. And so we have the ordered pairs 1, 3, 4, negative 1, negative 3, 0, 4, negative 3. We can also find the domain here by looking at the first components of these ordered pairs. We have 1, 4, negative 3, 4 as first component. So it looks like we only need to list negative 3, 1, 4. The range then is the second components, which would include the values 3, negative 1, 0, negative 3. And I'll put those in order, negative 3, negative 1, 0, 3. It's not incorrect to put them not in order, as long as you've got all the 4 values in those little brackets there. Okay, so let's go on. We found the domain and range of both of these relations. Here I have the relations again with their domain and ranges listed. And we're going to look at something else here. Some other words that we might use to refer to a domain. We might refer to the elements in the domain as input values or inputs, and the elements in the range as output values or outputs. Additionally, usually the domain, if we have x and y values, the domain is going to include x values. That's not essential, but usually that's the case. And the range would include y values, which for this second example of a relation definitely looks like it's the case here. An x value is, in this case, if an x value is representing values in the domain, x is going to be what we refer to as the independent variable, and y representing values in the range would be the dependent variable. Okay, so let's go on to the important thing that we're looking at in this section and throughout the entire course. All of college algebra and all of trigonometry, we're interested in functions. A function is a special kind of relation in which any 2 ordered pairs with the same first component also have the same second component. So let's look at the example of a relation, the first example of a relation we looked at, the set of ordered pairs 2, negative 5, 1, 3, 0, 2, negative 4, 3. Let's determine if this relation is a function. Well, what we have to make sure of is that any 2 ordered pairs with the same first component also have the same second component. In this example, we don't have any repeats of first components, so this would definitely be a function. There's no check here that we have to do. In the second example of a relation we have, notice that we have the ordered pairs 4, negative 1 and 4, negative 3. So in this example, we did have 2 ordered pairs with the same first component, and these 2 ordered pairs do not have the same second component. So that tells us that the second relation is not a function. Okay, so let's go on. an example of a function that I like to keep in mind is months of the year. And is this a function or is it not? So if we look at the months of the year and the number of days in each month, which you can probably use some trick. Students sometimes use their knuckles to count off the number of days. If you don't know how to do that, you could get someone to help you. Or I have a rhyme that I remember. 30 days has September, April, June, and November. All the rest have 31 except February. And February has 28. So that's not all of the rhyme, but it's most of it. So if we look at this example and we think of the months as being the domain, and the number of days in each month as being the values in the range, then we do have a function, right? Each month is different name here and is associated with exactly one value in the number of days. But if you finish that rhyme, and so 30 days has September, April, June, and November. All the rest have 31 except February, which has 28 days and 29 days in leap year. So actually February gives us a mess up to our example here. So if we think of February as having 28 days, then we do have a function. But if we think of February, which actually doesn't always have 28 days, it sometimes has 29 days, then this example is not a function because we have a value in the domain that is associated with more than one value in the range. So this is not a function. Sometimes it's just good to have little examples from real life that help you remember facts about the mathematics behind things. So, okay, so an equation representing a function. So an example of an equation that does represent a function is y equals 2x minus 3. How do we know this represents a function? Well, it actually represents a function of y. It represents y as a function of x. The way that we know that this represents a function is if we think of x as being the first component here and y as being the second component of the values that are determined by this equation, then the first component of x, any value that we put in for x is going to result in exactly one value of y. There's no way we're going to get two values of y here. For example, if I put in, say I let x be equal to 1, then y would be 2 times 1 minus 3 or negative 1. Whatever value we put in for x, we're only going to get one value for y. So this would be an example of a function, an equation representing a function. Remember, x is the independent variable, y is the dependent variable. So to determine if the following two equations here represent functions, we again are thinking of x as the independent variable and y as the dependent variable. So what we want to know is if I put in a value for x, if I choose any value I want to for x that happens to be defined for this equation, then do I get exactly one value for y, or might I get more than one? So the way we determine this is I'm going to solve for y here. So I have x plus y squared equals 5. That's the same as y squared equals 5 minus x, or y would be equal to, remember, plus or minus the square root of 5 minus x. Okay, so this isn't looking good as far as being a function, but let's try a particular value. Let's say I let x be equal to 1. Then if x equals 1, y would be equal to plus or minus the square root of 5 minus 1, or the square root of 4, or y would be equal to plus or minus 2. That means we have the two ordered pairs, 1, 2, and 1, negative 2. And that tells me this is not a function because I have the same element in the domain that is related to two different elements in the range. Well, let's look at this other example, an equation x squared plus y cubed equals 5. Again, the way to determine if this is a function is let's solve for y. Y cubed equals 5 minus x squared. And in this case, y would be the cube root then of 5 minus x squared. Remember, 3 is an odd number. And so any value, actually, I choose for x because we're taking the cube root. An odd root is only going to result in one value for y. Let's say, for example, x equals 2. If I put in x equals 2, then I'm going to get y equals the cube root of 5 minus 4, the cube root of 1, which is 1, positive 1. What if I let x be equal to 3? If x equals 3, then y would be equal to the cube root of 5 minus 9, or the cube root of negative 4. Oh, did I get that right? Cube root of negative 4. Okay, I actually thought I had a nicer number here that I could actually take the cube root of. But there is only one cube root of negative 4, and it happens to be a negative number. So this first example was not a function. And the second example, this equation is a function because any value of x results in exactly one value of y. Okay. And now we're going to look at the vertical line test for determining if the graph of a function, if a graph represents a function. Okay, so the vertical line test, a graph represents a function if no vertical line intersects it at more than one point. Which of the following relations represent y as a function of x? Okay, so let's start here. So how do we do the vertical line test? Well, we just imagine sketching any possible vertical line through this graph and looking at how many times the vertical line crosses the graph. And in this case, there's no vertical line I can draw that is going to cross that graph more than once. So using the vertical line test, no vertical line intersects the graph at more than one point. So we can definitely say that this is a function. I can't write very good. I'm still getting used to this semester. This is my first recording I've done. So, and you may find mistakes in these. If you do, let me know. I'm definitely not perfect, but I try to do the best I can. Well, this second example, this looks a little bit different. The first was had an infinite number of points in our graph there. This has a finite number of points. And in fact, we can draw a vertical line through two of these points. And this vertical line right here is going to cross through the points negative 3, 0, and negative 3, 1. So we're going to say that this is not a function because we have a vertical line that intersects the graph at more than one point. So this is not a function. All right. Well, one thing I found from teaching live classes of college algebra is that a lot of students have kind of draw a blank when we start graphing equations of lines. So this is an equation of a line. Let's just do a quick review of how we would sketch this relation 3x minus 2y equals 6. What we're going to do is we're going to sketch a graph, and from the graph we're going to determine if this relation is a function. So if I want to sketch the line represented by 3x minus 2y equals 6, I usually like to find the x and y intercepts on an equation that looks like this. So if I let x be equal to 0, then negative 2y would equal 6, or y would equal negative 3. Then if I let y be equal to 0, then 3x equals 6, or x equals 2. So if I then just plot the 2 points 0, negative 3, 2, 0, and sketch a line that passes through those 2 points, we have it. So is this relation represented by the graph here, is this a function? Well, if you look at sketching any possible vertical line through this graph, any vertical line that we can draw is only going to cross the graph one time. So we can say, yes, this relation is a function. All right, and now throughout these lectures or these video lectures, I guess you would say, I'm going to have some problems that I want you to try on your own. And this is the first one. I want you to graph the following three relations. From your graph, determine if the relation represents y as a function of x. Okay, so do this on your own. The first graph is y equals 3. The second, y equals 2x minus 3, and the third, x equals negative 2. If you need to pause the video for just a minute, you can do that and just write these down. So make sure you've done this before next class so that we can talk about this in our next class. Okay, and then we're going to look at determining the domain and range of a function from a graph. So, and I am moving on to where these are only functions that we're going to be looking at. So if we're looking at determining the domain from a graph, we're looking at this first graph. I'm looking for all the x values for the domain. So domain, we think x. So if I could take this graph and smash it down so it lies along the x-axis, notice these arrows here mean the graph keeps going to the left and to the right. Then if I could smash all the points on this graph onto the x-axis, it would actually cover all the points on the x-axis. And so my domain here is going to be negative infinity to infinity. I think I put both the domain and range here. So we could cheat and just look at the range. But let's see where we get that range from 0 to 4 from. Okay, so the range, let's erase the x values here. And then if I want to look at the y values, remember the range represents y values. If I can think of smashing this graph onto the y-axis, I'm looking for all the y values that appear on this graph. So our smallest y value is actually going to be bigger than 0 because this graph is approaching the x-axis, but it's never actually touching it. So we know that whatever y is going to be greater than 0. It's going to get super close to 0, right? But it will always be a little bit bigger than 0, which means we're going to start with a curved bracket, then 0, 4, and then notice that we actually do include this y value of 4 here, so we use the square bracket. So we go from y being greater than 0 up to y equaling 4, and then we stop. And we include that point of y equals 4. So that's the domain and range from our first example. The second example, this is a messed up looking example, so I actually thought it was a good one to look at here. If we're looking for the domain, and we're looking for the domain is all the x values, then let's see what we have. If we think of smashing this graph onto the x-axis, we're going to still be missing this point at negative 3, right? So we'd have all the x values be starting at negative 5 up to negative 3, but not including negative 3. And then if we smash this lower part of the graph up onto the x-axis, notice that we actually cover the point negative 1 here. We cover all of the points along the x-axis until we get up to 3, where we do not include that point 3. So the way we would write the domain here is negative 5 with the square bracket, meaning we include that point negative 5 up to negative 3. We don't include negative 3. We have a hole in our graph at that point. Union negative 3 all the way up to 3, and then also we have a hole at the point where x equals 3, so we're not going to include that point. Okay, so that's the domain, and again we're kind of cheating here, looking at the range before we figured out what it is. Okay, so let's see how we would determine that range, which is the y values. So the range, we're going to smash our graph onto the y-axis. When we bring this point negative 3, 4, the missing point onto the y-axis, it's still missing here. But the point at y equals 0 is going to be a solid point there on the y-axis. So we're going to have everything from y equals 0 up to y equals 4, not including 4. So that would give us that, it gives us actually the second point here. It gives us from including 0 up to 4, but not including 4. So this is the second part of the graph here. And then we're also including from negative, if we smash this lower part of the graph onto the y-axis, we're missing -2, and we're missing -1, but we have all the points in between there that cover y values. And so that's going to be -2 to -1, not including the points -2 or -1. Okay, so one more here, and this graph is the graph of a finite number of points. It looks like we have 6 points here, and so to find the domain when we don't have connected lines here, when we just have points, we're going to make a set notation. So we use brackets here rather than the interval notation like we've been using for these other two. We use brackets, and we just include for the domain the x values included on these points. Like this first point would be -4, -1. So for the domain, we just include the x value of -1 or of -4, then the x value of -3, the x value of -2, -1, 0, and 1. And then for the range, we're looking at the y values. So we'd have -1, 0, 1, 2, 3, and 4. And so that's our domain and range. And remember, don't be afraid to use the curly brackets there. That's what you need to have the set notation correct. Okay, so let's go on. Function notation is pronounced f of x. And I know you've probably seen this before. You may have seen this diagram before. This just is kind of a diagram we like to use to represent what function means. We have our domain here, which includes our input values. We have a value x in the domain, and this function, some operation f, takes our value of x into the range, which includes our output values, and here y equals f of x. And remember, we would only have one y value associated with this x value. So for a function, we have one x value, and our function takes that x value from the domain into the range and assigns it one value, which is our output y value. Okay, so you've probably found function values before. Here, if we went to find f of 5, where f of x equals the square root of x minus 1, f of 5 would be equal to the square root of 5 minus 1, which is the square root of 4 or 2. Okay, so that's a fairly simple problem. A similar problem is for f of x equals square root of x minus 1, solve f of x equals 5. So this is a different problem. We're not plugging, remember before we found f of 5, here we were letting x be equal to 5 and we were figuring out what y is. In this second case, we're letting y, f of x, you can think of as being the same as y here. We're letting y be equal to 5, and we're trying to figure out what value of x would give us that y value. So 5 equals the square root of x minus 1. We can square both sides to get 25 equals x minus 1, and then add 1 to each side, giving us 26 equals x, and we usually like to write this as x equals 26. So that is our solution here. It's the solution to f of x equals 5. And try on your own number 2. So this is the second problem I'll have you try on your own here. We have for f of x equals the square root of x minus 1. Oh, is this the same? Find f of 5. I think this is the same problem I just did. Well, you should have an easy time with this one then. So you're going to find f of 5 and then solve f of x equals 5. Let's change this a little bit. I'm going to change this. Let's let f of x equal x squared. Okay. And if f of x equals x squared, let's find f of -3. And then let's solve f of x equals 25. Okay. Okay, so I'm going to change this problem a little since I messed this up, and that's going to happen occasionally. And so go ahead and write this down. And I'm going to make a note of this as well, hopefully. So I have f of x equals x squared, and we're going to find f of negative 3, and then we're going to solve f of x equals 25. Okay. All right, let's go on then. Finding the domain from a formula. Okay, so we're doing a bunch with domains and ranges and functions and so forth. And so when we're finding the domain from a formula, we're using a little bit definition here because we started with defining a domain using a relation. And now that we're definitely into functions, we're going to say the domain of a function is the set of all input values for which the function is defined. So if I'm looking at finding the domain of the function f of x equals 2x plus 3, I'm finding all x values or input values for which this 2x plus 3 is defined. So what values of x can I put in here? Well, actually, let's do an example. I could find f of 1 would equal 2 times 1 plus 3. In fact, any value I want to, I'd get, what, 5 there? I can put in any value of x I want to. There's no restrictions. This is it would be the equation of a line if we graph this as a line. But f of x equals 2x plus 3, a linear function. We can also think of this as a polynomial function. It's a simple polynomial function. This is going to be, the domain is all real numbers. Sometimes we do a double barred R to write all real numbers, but usually we like to write the domain in interval notation, negative infinity to infinity. And always with infinity, we have those rounded brackets on each side there. And also, just because I've seen some students have problems with this, always when you're writing interval notation, the smaller number comes first, the bigger number comes second. We go from left to right. Okay, so the domain of any polynomial function or any line is, I shouldn't say that. No, you'll actually see and you try on your own. So there are some lines for which the domain is not all real numbers. Okay, but, okay, so let's go on. Okay, so find the domain of the function g of x equals 1 over 2x plus 3. So you guys have done these before. When we have a fraction, what we have to be careful of is that the denominator is not equal to 0. So we want to make sure that the denominator is not equal to 0. Okay, well, what would make this denominator equal to 0? Let's see, if 2x plus 3 equals 0, then 2x equals negative 3, or x equals negative 3 halves. So we need to make sure that x is not equal to negative 3 halves here, but there's no other restrictions on this particular function. So we could write this in set builder notation, the set of x such that x is not equal to negative 3 halves, or interval notation, negative infinity to negative 3 halves, union negative 3 halves to infinity. Okay, so that's our domain of this function g of x. Then we have the function h of x equals the square root of 2x plus 3. We want to find the domain here. So if you remember a square root, whatever's under that square root sign has to be greater than or equal to 0. Okay, and I suggest you start by writing it this way. I found a lot less mistakes if you put in that extra step of writing whatever's underneath the even root sign being greater than or equal to 0, and then solving. We end up with x is greater than or equal to negative 3 halves. In interval notation, that would mean we're starting with negative 3/2, including negative 3/2, and then we go up to infinity, and remember we always have a rounded open bracket there. Okay, so this is the domain of h of x. Then we have capital F of x equals 2 over x squared minus 4. The only restriction we get here is from this being a fraction, we want to make sure the denominator is not equal to 0. Well, x squared minus 4 is the same as x minus 2 times x plus 2. And the only values of x that would make that 0, we want to make sure that x is not equal to 2 and x is not equal to negative 2. Okay, so we can write that in interval notation as negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Remember, we always go from left to right, from smaller to bigger, and so we have the domain here. Now we have a similar looking function, capital G of x, 2 over x squared plus 1. If you look at x squared plus 1, there's actually no value of x you can put in here where you're going to get 0. So x squared plus 1 is never equal to 0. No value of x is going to make it that way. So if there's no value of x that makes x squared plus 1 equal to 0, this function is actually defined for all real numbers. So the domain here would be negative infinity to infinity, and we're done. Okay, then, one that's just a little bit more complicated. We have capital H of x equals the square root of x over x minus 1. Well, from the x minus 1 in the denominator, we know that x cannot be equal to 1, right? Or that would give us a 0. From the square root of x in the numerator, we know that x has to be greater than or equal to 0. And so our domain here, well, let's see. We know for sure that we have to be greater than or equal to 0. So we'll start at 0. But we can't have a value of x being 1. So we go from 0 to 1. Union 1 to infinity, and that is our domain here. Okay, and we're just about through today. We have one more try on your own, and this one is to find the domain of h of x equals the square root of x plus 1 over x minus 5. Write your answer in interval notation. And that's it for today. So work through these try on your own. Let me know if you have questions about anything, and have a wonderful rest of your day.